So now we're going to solve a question, and this one's taken from exercise 1B of the Hazy and Harris textbook, Qu1d, and this is the question where we have to show that this, for all cases of positive integers, is divisible by 3. So let's start off using our skeleton or framework that we talked about earlier, and let's look at n equals 1. So replace n with 1 and see if it's true. 7 to the 1 plus 2 times 4 to the 1. Well, we know that's equal to 7 plus 2 times 4, which is equal to 7 plus 8, which is 15. And we know that's divisible by 3 because 15 is equal to 3 times 5. So therefore, P1 is true. Done. Now we're going to look at PK. So we're going to assume that that's true. So we're going to assume that 7, instead of writing n, we're going to write k to the k plus 2 times 4 to the k is divisible by 3. How do we write that? Well, if it's divisible by 3, we're going to say that it's a multiple of 3. A bit like here, where we said it was a multiple of 3 times 5, we're going to say it's 3 times a number we don't know. And that's okay, we're going to assume that's true. Now we're going to find pk plus 1. Follow the same process, but instead of writing n, we're going to write k plus 1. 7 to the k plus 1. Okay. At the moment, that doesn't look very similar, but we got our indices laws which we can use, and we know that that's the same as saying 7 to the k times 7 to the 1. Our indices laws number 1, where if we have the same base number, then the powers become added. So I'm just working that in reverse. I'm just going to write that a little bit differently because we want to use 7 to the k. So I'm just going to write that a different way around with the numbers first. So that will become and y8 because 2 times 4 is 8. Okay, now we're going to use pk, and we know that pk is this here. This is pk. So can we get that in there? Well, yes we can. If we factorize it, then we can put it in there. We can almost sort of force it in there. And that there becomes that here. So we're using this pk. Now the problem is, this is okay. It gives us 7 times 7 to the k, which is what we want. It also gives us 14 times 4 to the k, and we only want 8. We don't want 14 of them, we only want 8. So we're going to take away 6 of those. Now we still have to prove that this is a multiple of 3. Well, we know that this is there, and that's a multiple of 3. So we can say that this is true. And we know that 6 is made up of 3 times 2, which we also know is a multiple of 3. So we could also factorize that if we wanted to, and quite easily show that this is a multiple of 3. There we are, we've showed it's a multiple of 3. Hence, pk plus 1 is a multiple of 3. And then we would write this closing line, since P1 is true, showed that here, and pk is true, if or whenever pk is true, then Pn is true for all n belongs to positive integers. And there we have it. Tick.